Anton Kapustin today from Caltech, who's going to talk about superconformal field theories in 3 dimensions with almost maximal supersymmetry.
So thank you for allowing to speak here. So I'm going to talk about field theories with in 3 dimensions with maximal supersymmetry, and also, if you say a few words about theories which is slightly less than maximal supersymmetry. That's the reason for the word almost. Well, the motivation is this. So if you think about theories with maximal supersymmetry, they typically think about as showing some high degree of uniqueness, and the intuition comes from 4 dimensions mostly. If you think about theories with maximal supersymmetry in 4 dimensions, we think we know all of them, and they're all very simple. They're so-called n equals 4 super Young-Mills theories.
Recall what the n means?
I'll discuss it later. Yeah. But maximal supersymmetric means the largest reasonable number of odd generators in the superalgebra. And in 4 dimensions, such theories are very unique. So at least we believe so. There's no proof, but I think we know already all of them. And I'm going to review what's happening in 3 dimensions this talk, and we'll see the situation is much less clear. So perhaps there is some simple classification scheme, but so far it sort of evades us. So I'll begin by describing what superconformal symmetry is in 3 dimensions, and then I'll review some ways to construct superconformal field theories, and then catalogs the ones with the highest degree of supersymmetry. And then we'll see that the situation is actually rather complicated, because what you see is not always what there is, right? Sometimes there's more than what you see, and that's why you have this hidden supersymmetry sometimes. And then I'll discuss some examples, and then the last part I'll discuss some general results on theories with almost maximal supersymmetry. So first of all, let's begin with conformal symmetry. Well, conformal symmetry is some extension of the Poincare algebra, and so we have let's see, a pointer or something. Is there a pointer somewhere? I guess not. Not that long, unfortunately. Okay. So anyway, so there is a. Okay. Use this arm. Okay. So there are generators of Poincare algebra, which are like momentum generator P mu, and this rotation generator M mu, which is antisymmetric in the low indices. But then there are some more generators. There is a conformal boost called K, and then there is a dilatation generator, the one sort of responsible generates rescalings. So and you join new commutation relation, which basically says that momentum has dimension 1, boost has dimension -1, and then the most important relation is this one, which says how P's and Q's commute. Okay. So it's conformal symmetry, and roughly speaking, it's a symmetry of a system which is scale invariant, although of course there's actually some distinction between scale invariance and conformal invariance, but for most parts we just think about as a symmetry of a scale invariant system. Well, if you want to add supersymmetry, then you add some odd generators to this algebra, and there are there are n odd generators of dimension 1/2 and n odd generators of dimension -1/2. So the one with dimension 1/2 is called Q's, and the one with dimension -1/2 called S, so the total of 2n odd generators. Well, more precisely, 2n odd generators, each of which is a spinor. So a spinor in 2 dimensions has a real dimension 2. So we have multiply by 2 if you want to know the actual number of odd generators. And then also these generators, there are n of them of dimension 1/2. So there's a SON symmetry which acts on them. It's called R symmetry. So, and the important accommodation relations are written here. So there's the usual supersymmetry. That's sort of the other copy, if you wish. And then there is the most important one is this relation between supersymmetries and their sort of evil twins, the S's. Okay. So now the algebra exists for any number for any n, for any capital N. But if you want to have a reasonable field theory, interacting field theory, then you want to make sure that there are no conserved currents of spin greater than 2.
Symmetry generators?
I do. Well, here.
Oh,
So I forgot to mention, they also are symmetry generators.
And that G should multiply delta.
Yeah. Sorry, forgot. Yeah, that's right. So, so okay, the question is, okay, the maximal possible supersymmetry is n equals 8. You know, the one which contains particles up to spin 2, not higher. So first of all, and so that's what's called maximal superconformal symmetry. And the question is, how many such theories are there? Can we classify all of them? Yeah.
In 3 dimensions?
Well, in any dimensions. One stress energy tensor, nothing, no conserved currents of higher spin.
N equal 8, you don't you spin 1. You take n equal 4 super n.
No, I mean the multiplet of a stress energy tensor doesn't involve any higher spin currents. So that's you want to make sure. Okay, so well, first of all, well, how do you construct any such theories? Well, we can first of all forget about superconformal symmetry, drop some of the generators, and just look at these Q's and P's instead of all of them, and look for a theory which is not conformal, and then with the same number of Q generators. So and the easiest way to construct such theories is to look, one standard way to look at what's called super Young-Mills theories. So, let's see, I have chalk here. Okay. So that is, you want start with a gauge field and write some action. Start with an action like this for the Young-Mills part, well, times some dimensionful coupling. In 3 dimensions, dimensionful, and then add other fields and terms to make the whole thing supersymmetric. That's what I call super Young-Mills theory, and such theories exist for, I guess for n equals 1, 2, for n equals 1, 2, 4, and 8 supersymmetries. And in particular, if you want n equals 8, the action is completely fixed once we choose the gauge group G. So the action, one also chooses dimensionful coupling. But, so this part is just like in 4 dimensions. We have maximal supersymmetry fixes everything. But, well, this theory doesn't have superconformal symmetry. For example, it's R symmetry group, which acts on the spinners, on the supercharge is actually SO7, or spin 7, not SO8. And it
theory is unique. That's, you write that there's a unique Lagrangian.
There's a unique Lagrangian, yeah. Okay. Up to this overall factor. So, so the supercharge is again in the wrong representation. First of all, in the wrong group. So it's SO7 instead of SO8, and also then the spin representation, which is also 8-dimensional, but somehow once you go to the infrared limit, the number of supercharges remains the same. That you still have 8 of them of dimension and a half, but they sort of must reassemble just by, they have to, if the superconformal fixed point exists, into 8-dimensional representation of SO8. So sort of R symmetry gets enhanced to SO8. So, well, this field theory is actually, the superconformal field theories you get in this way are very complicated, well, hard to understand, because you start with something nice and sort of classical, and then you let it flow to the long distances. Then at long distances, interactions become very strong and you have no control of what you get. So you get some field theory, but you're not sure how to compute anything in this field theory.
That enhanced R symmetry is part of the algebra that you wrote down?
Yeah, it has to be. Yeah, once if you have superconformal symmetry, you have to have SO8.
It's SO8.
So if you believe that Q's remain supercharges in infrared theory, then the R symmetry must get enlarged to SO8 from SO7. Okay. So and then there is a non-standard embedding of SO7 to SO8, so that that 8 vector, so 8 spinner becomes 8 vector of the SO8. So, well, basically related by triality to the usual embedding. Now, this theory, well, first of all, it's not even true that, okay, suppose you pick one of these Young-Mills theories. It's not even true that that you get a single superconformal fixed point long-distance theory if you start with it, because what you flow, well, the long distance might depend on, these theories have not a unique vacuum, but whole moduli space of vacuum, and the infrared limit depends on where you are in the vacuum moduli space. So, but like the moduli space, actually this, it's basically 7 copies of the Cartan times 1 copy of the maximal torus divided by the Weil group. So one can get more than one superconformal field theory from the same Yang-Mills theory, just depending on where you are in the modular space. Like in particular, well, let me just, for example, start with the, well, if you start with G equals UN, for example, then, well, there are several special points in this modular space where the theory, so as classically has an unbroken gauge group, but actually there are endpoints like that. But at all of these endpoints on this modular space, the theory flows actually to the same conformal field theory. So basically, it's unique interacting superconformal field theory. But if you start with, say USP2N, you don't get a unique answer. So there are 2 different fixed points, 2 different long-distance theories you can get. And so in the modular space, there are 2 special points, and that so point A and point B. And the long distance is actually different. Long distance limit is different for these 2 points. So while for this type, you get 2 copies of the same field theory, and also for this theory. So in these 2 cases, you get 2 copies of the same superconformal field theory, but for this one, you get 2 different ones. And actually, it so happens that they're the same pairwise. So there are 3. Actually, like for fixed n, you get not 3 different theories, but only 2, which is known by A and B. So now, how do I know that? So I told you that in the long distance limit, the theory becomes strongly interacting. Oops. Yeah, the point is that say for n equals 4 superangles, there's a unique point.
Yeah, it's in 4 dimensions.
Here you have, yeah, it doesn't have to be. The interesting thing is though that some of these points are actually equivalent. And how do I know that? How some of these long distance limits are equivalent? How do I know that? Because if I start with the gauge group, they look totally different. So how are they related? Well, to see that, you need to use some other input. And for example, you can use string. Well, actually, that's the only way I know is to use some string theory. And the point is that each of these theories for classical gauge groups can be realized by some system of n M2 branes and some particular background. And it turns out that, well, so these points in the modular space corresponds to a station when all n M2 branes are basically on top of each other. So, the difference between these cases, I'm just called C maybe, is that this fixed point corresponds to a station when you have n M2 branes in flat space-time, which are all on top of each other. Here we have, and these 2 guys, A and B, corresponds to n M2 branes on the manifold of this sort. Rather than flat 11-dimensional space-time. So in the reason that there are precisely 2 possibilities in this latter case is because there is some basically there is some 2 different kind of orbifolds in M theory, different by some discrete torsion in some cohomology group, basically in H4 of, well, if you look at the neighborhood of this orbifold point, you have RP7, and so you look at this group, and then it's actually Z mod 2, so you have two options there. And that's why you get, there are two field theories that you can possibly get, and then some further analysis from string theory shows that, in one case, you have torsion classes the same in both cases, about both points. Here it's opposite, and here it's again the same but different. So it's some string theoretic argument. Well, that's great, but what about other gauge groups which are not classical? Like if you look at exceptional gauge groups, for example. They also flow to some superconformal field theories. Well, are they all different or the same? I have no idea, actually. So it's not clear. So now, well, in some cases, you know that there's only one point. Like for UN, for example, there's only one. Well, like for, if you look at, let's say, G2 or F4, there's only one special singular point. So there's some superconformal field theory. But for other cases, I don't know, maybe there's several different ones. So, so the situation is already complicated, but there are other ways to construct this n equals 8 theories. So instead of, well, I can try to add Chern-Simons term here. And then try to supersymmetrize the whole thing. Well, that actually works only for low degree of supersymmetry. Namely, well, up to n equals 3 supersymmetry. And if I want to get n equals 8, that doesn't work. Actually, it doesn't even work if I want to get n equals 4 supersymmetry. But actually, the situation gets better if you just drop the Maxwell terms completely and start with the Chern-Simons term and then try to supersymmetrize that.
So is the statement that you don't have a right down?
On something that has.
Well, one can show that any Lagrangian you can write down which involves both of these terms cannot have larger than n equals 3 supersymmetry. So, but it was discovered actually rather recently that if you drop this term, then there are many more possibilities, and you can get higher supersymmetry starting just from Chern-Simons. So, so in this way, one can construct theories with n equals 4, n equals 5, n equals 6, n equals 8 supersymmetry. Now, what about n equals 7? So you like number 7. It's a lucky number. What happened to it? Well, actually, in this case, this number is not lucky because there are no theories with n equals 7 supersymmetry. And my last slide, I'll explain why. The recent result. But let me now discuss the other cases. Well, my goal is actually to look at n equals 8, but first let me describe some cases with lower supersymmetry. Well, n equals 4 construction is pretty simple. So if you want to construct n equals 4 supersymmetry, is supersymmetric Lagrangian, you're supposed to start with well, start with some n equals 3 Chern-Simons theory, and then try to tune your representation and the gauge group so that the result actually has n equals 4 supersymmetry. That was basically the approach of Guyot and Witten. And it turns out that what needs to be done is you want the representation in which the matter fields transform together with the gauge group fit into a Lie supergroup. Moreover, not just any Lie supergroup, but the one which has non-degenerate invariant bilinear form. Okay, so there's some reason behind it. I'm just going to explain that. So now there's some generalization of this construction where instead of trying to complete your gauge Lie algebra to superalgebra, you try to complete it in 2 different ways. If you manage to do that, you can. Well, the case which you get to constructed corresponds to the case when you choose one of the super Lie algebras. You get in this way to be like just the original Lie algebra, and the other one to be some non-trivial extension. But if you sometimes you can manage to do it in, well, first you can just well, there are more general ways. You can, starting with a given Lie algebra, you can enlarge it to a Lie superalgebra in several different ways usually. Then you get more general theories. Now, one can, in this way, one get also n equals 5 supersymmetry. That wasn't really possible in Guyot-Witten construction, but here it's possible. One just needs to choose these 2 representations to be the same. If you manage, well, so that's basically because you want SO4 R symmetry to be enhanced to SO5, and the spinner. So they're sort of, well, these 2 guys form representation of. They both transform representation of SO4, different ones, but you want them to assemble into representation of SO5, and in different representations of the gauge group, that cannot happen. So I don't know, make a complete list, because there's some classical examples like these ones, with gauge group is UN cross UM and ON cross USPM. In this case, the least choice of Lie superalgebra which completes them is obvious. So in this case, it would be the general linear super Lie algebra. In this case, OSP superalgebra. But there are also exceptional examples. The exceptional Lie superalgebras which also correspond to some Chern-Simons matter theories that I'm going discuss that. But for n equals 6 situation is much simpler. For n equals 6, well, there are only two choices basically, three infinite series. Okay, so there's a O2 cross USP, UN cross UM, and SUN cross SUM. So these are the only theories with manifest n equals 6 superconformal symmetry. So that's complete classification. And it's non-trivial, but it's a closed form answer because we can analyze all possible classical Lagrangians with a given symmetry. Now, and further, if we want actually n equals 8, situation is seems even better or it's simpler, because if you look at which of these theories actually have n equals 8 supersymmetry, well, that is basically only one choice. G should be SU2 cross SU2. And actually, historically, these examples are discovered first, and all these theories with n equals 4, 5, and 6 were discovered later. But
A quick question about
yeah,
I always was confused. I mean, the K gets shifted, right, in one loop because of fermions, but shifted always. I mean, K will become, let's say, K plus, and minus K will become.
so in this case,
This will not.
this K is before integrated out fermions, sort of. So the fermions also shift the level. So
Right. But they will. I mean, this relation will not remain asymptotic, K and minus K.
no, it remains. It remains. The fermions shift the level by this amount proportional to sine of K. So they shift in the same direction. So
Doesn't matter. Okay.
they shift in the same direction.
Yeah.
That is, yeah. So, okay, it seems simple enough. So we have basically one case up to choice of this integer level K of which gives us n equals 8 Chern-Simons matters theory. And these theories are called BLG theories, and the interesting thing, they're weakly coupled for large K. And along with the infrared limit of n equals 8 super-Young's theories, this is the only known n equals 8 superconformal field theories. But actually, the situation is not as simple as this might seem, because soon after these constructions, it was proposed by Aroni, Bergman, Jafferis, and Maldacena that actually one of these n equals 6 theories, which has been written down, well, actually, they wrote it down too, but they proposed actually this theory, first of all, has a string theory realization, and second, for special values of this Chern-Simons level, 1 or 2, it actually is supposed to have hidden non-manifest n equals 8 supersymmetry. This supersymmetry is not there on the classical level, because we know classical all has n equals 6. There's nothing you can do about that. But the proposal was that, well, that on the quantum level they have n equals 8 if the level is chosen to be 1 or 2. So one reason for that is you could well, they propose that this theory describes M2 branes on this orbifold, and for k equals to 1 or 2, that orbifolding preserves supersymmetry, full supersymmetry. But there is also they sketched the field theory argument, which I'm going to expand on later, explaining why there's some quantum symmetry in this theory, which is larger than the classical one. Well, the conjecture also is that, this n equals 8 superconformal field theory actually is not new. It's actually isomorphic to the one you get from super-Young's theory with gauge group UN. So it's not really new, but it's a new construction. And that, of course, raises all kinds of issues, because if we found one example where supersymmetry is not what it seems, it's larger, maybe we missed a whole bunch of other examples too, because classically maybe supersymmetry is n equals whatever, and quantum mechanically it gets maybe much bigger, maybe even n equals 8. But there are no such examples in four-dimensional field theories. They're typically, nobody knows any examples where supersymmetry is enhanced in a non-trivial way from, I don't know, maybe from n equals 0 to n equals whatever, but or n equals 2 to n equals 4, something like that. But in 3 dimensions, as we'll see, it's actually quite common. So the situation is much more complicated on the quantum level.
There is no like dimensional CMT for K, and then you can switch.
Well, there is something like that. We'll see
Because
something.
once you choose K equals 1 and 2, there can be other K.
So I'll discuss some things like that. Not quite like that, but yeah. So now there's actually a further thing. So there's a later paper which proposed that these other n equals 6 theories with unequal ranks also have an M theory interpretation, and well, in this case the difference between the ranks cannot be larger than K actually, to to avoid some spontaneous supersymmetry breaking, but suppose it's in that range, then the conjecture that this theory that describes some brane system in string theory implies that, for example, this theory, which has n equals 6 symmetry, actually also has n equals 8. Okay. And that seems rather strange. First of all, this theory doesn't seem parity invariant, although I don't know any theorem which says that maximal supersymmetry should imply parity invariance of the theory, but all the theories we know so far, and all maximal supersymmetric theories, always parity invariant. Because basically the multiplets are parity invariant, so it's not clear why. Well, it's not clear if one can arrange. Well, the fact that particles are in parity invariant multiplets doesn't mean that you cannot arrange maybe interactions which are not parity invariant, but still it looks suspicious. So this is another example of hidden n equals 8 supersymmetry. Now, how is this established? So the argument was actually sketched briefly in this original paper of ABGM, but was later worked out in much more detail by my student Denis Bashkirov and myself. And the idea is to use monopole operators. So but first you can ask, how can a quantum symmetry be larger than classical symmetry? It's more typical to have actually quantum symmetry smaller than the classical symmetry. And to quantize a classical system, you should be wary of some anomalies, which you won't be maybe able to preserve all of the classical symmetry on the quantum level. That's more familiar situation. Here, quantum symmetry is bigger than the classical one, and the reason is that there are certain operators which quantum mechanically count as charges, but classically they don't count as charges. And or in field theory, they're local operators which quantum mechanically count as conserved currents, and classically they don't. So how can it be? Well, in this case, but for this three-dimensional theory, is a very common example of something which doesn't count as an operator in classical theory, but does in the quantum theory. It's called disorder a monopole operator. So basically take any gauge group, and the action doesn't matter. So, well, the point is that you can think about the local operators that disturbance at a point, and in particular, you can imagine that the disturbance is so big that the fields are singular there. So you can imagine that near this point, the gauge field strength, well, the magnetic field sort of is like this, the radial one, so that this is magnetic field flux is 2 pi n, sort of insert Dirac monopole. In other words, what this means is that the gauge field is singular near this point. If you denote the r by r, the radial distance to this point, then it is divergent part, and the rest is smooth. Okay. Well, I described it for U1 theory. That's what it means to have a Dirac monopole at a point, but you can generalize it to non-abelian case. You just need to choose an embedding. Choose some homomorphism rho from U1 into your gauge group, and then use this embedding to embed this configuration into your non-abelian gauge theory. Well, of course, this embedding, you can conjugate this homomorphism. So the important thing is that this homomorphism modular conjugation. So therefore, you get sort of monopoles are labeled by elements of the, well, if you call them, well, the maximal, you have maximal torus of the group. You can consider homomorphism from U1 to this maximal torus. It's called co-character lattice, and then you quotient by the Weil group. That's where this magnetic sort of charges live in an abelian case. Okay. So do I need to do anything? I guess not. Okay. So now this doesn't quite characterize your disorder operator. Okay, the gauge fields have this behavior about other fields, but the other fields might also be singular, and you can often fix how other fields behave by imposing supersymmetry. Now, it's much actually easier to think about the situation, not in terms of configurations of fields which are singular at some prescribed point, but rather using this trick called state operator correspondence. So if you imagine your space-time is Euclidean and sort of reinterpret the radial direction as time, which you can do after, well, then in use conformal symmetry, you can map this situation conformally to the following one, where you have the space-time is now S2, the sphere, across the radial direction, which is R. And you just have flux of this magnetic field through S2. And then in this situation, you can consider, so just quantize this theory on this compact space regarding R's time, so you get some Hilbert space. So that Hilbert space is identified with the space of local operators at the point. So that's called state operator correspondence. So instead of trying to classify operators with a singularity of gauge fields like this, you can classify states of a theory on a S2 across time with magnetic flux through S2. Now, of course, magnetic flux doesn't fix uniquely, a state. So the Hilbert space in a given flux sector is infinite dimensional, and you can, for example, you can pick a state which has the smallest energy, which, from the point of view of the operator, means pick the operator which has the smallest dimension. You also need to impose gauge invariance, of course, if you want to classify gauge invariant operators. Well, there's a problem with this approach is that this actual quantization, if you want to figure out, what is the dimension of the operator with the lowest dimension in a given flux sector, you need to be able to quantize this theory in a two-sphere, and this gauge theories are typically strongly coupled. So how do we do quantization? Well, if you just want to restrict to weakly coupled theories, you actually don't have, you're restricted quite a bit. You must either choose Chern-Simons coupling to be large, because that's when the theory becomes weakly coupled, or maybe the number of matter fields to be large. So, but you cannot just deal. But the interesting questions are precisely about theories with Chern-Simons coupling order 1. For example, ABGM conjectures about such theories.
This is typical in two-dimensional symmetries, right? They have operators which are classical and which are.
In 2 dimensions, much more common. Yeah.
So it's really. But it's exactly the same phenomenon, actually.
Yeah, well, but the question is how to compute with that. Yeah. So different methods are used in 2 and 3 to actually be able to work with this. For example, here, again, 2 dimensions have infinite dimensional algebras which help you. Like here you don't, but you have another approach. You can, if you have large supersymmetry, you can still manage to learn something about these disorder operators. And suppose I manage somehow to quantize the theory. So how I'm supposed to use this knowledge to establish existence of extra supersymmetries? So this is a bit roundabout. So I'll explain later why this roundabout way is what you need, but that's how it goes. First, we need to, we want sort of, the idea is the following. First, we need to establish that there are some accidental scalar states that corresponding to sort of spin 0 monopole operators with the dimension equal to 1. Now, acting on these scalar states with manifest supersymmetry generators, with the one which you know for sure are there, we get vector states with dimension 2. Well, each supercharge has dimension 1/2, so acting twice it gets dimension 2. Now, in a unitary conformal field theory, they must correspond to a conserved current if it's a primary state. So, furthermore, if we know which representations of the scalar states transform, we can figure out what the representations for these vector states is. And if they happen to be a non-trivial representation of supersymmetry, or of R symmetry, SO6, that means that these conserved currents are part of the R symmetry group, and R symmetry must be enhanced. And then you can show that it's enhanced at least to SO8. So that's how it goes. And once you know that R symmetry is enhanced to SO8, supercharges must also leave a larger representation than you thought. So they must leave an actually, not in a vector of SO6, but in a vector of SO8. And that's how I know that n equals 8 supersymmetry is enhanced. N equals 6 is enhanced to n equals 8. Well, it doesn't have to be n equals 6 to n equals 8. You can start with pretty much any supersymmetry and try to look for this enhancement. Now, why is it was important to look at the scalar states? Well, you see, when you try to quantize, if the theory is strongly coupled, you have to find some trick to do it. And what the trick is here is the following. If we deform the theory on this S2 cross R in a way which preserves only a small subset of symmetries. Now, but it's crucial to preserve at least one complex supercharged, which is squares to 0, because then one can argue that this Q closed states are preserved, well, which are not exact, are preserved under deformation. So you start look at the Q cohomology and argue that it doesn't change. The argument basically similar to Morse inequalities argument. Now, of course, you break a lot of R symmetry too, so you don't find all the states that you would like to find, but you find the important ones. And then you can argue, it's sufficient to argue that you have all of them in the undeformed theory. For example, let's look at n equals 6 case, which is of interest to us. So deformation we're going to break down to n equals 2 supersymmetry. And SO6 is broken down to SO2 times SO4, which SO4 commutes with the n equals 2 supersymmetry generators. Now, what are the accidental states? What are the sort of accidental scalar states we're looking for? Well, n equals 8 superconformal symmetry says that in the same multiplet as the stress energy tensor, there are scalars with dimension 1 in representation 35, which is anti-self-dual 4th rank tensor of SO8. Now, if you decompose this under this manifest symmetry, which is SO6 cross SO2, you get this. So these two guys you see right away, and but these two guys must be sort of the accidental ones, or the one which come from monopole operators. And this you see, this is SO2 is actually the is basically the magnetic charge, this flux through S2. So for 15, it vanishes, but for these two guys, it's non-zero. So it's monopole operators. So we're looking for scalars in this representation. So these are our accidental ones. Now, but the deformation which we're using actually breaks this SO6 symmetry too. Okay, down to this one. Okay, so we would like to find all these fellows here in the deformed theory. But actually we can't, because the one which we are able to find are the one which is called BPS scalars. These are the scalars which carry non-trivial, well, basically with the highest possible weight. So basically we can only look for these guys. But once you know that these guys exist, you can argue using that in the undeformed theory, they must assemble to some representation of SO6. So this guy, you can argue from that, it must also appear. So some group theory basically tells it once you establish existence of these two guys in the deformed theory, you know about this fellow and then also this one, and then you know about the whole thing. So here's an example how that works. So for k equals 1, for example, let's say BGM theory. So in this case, well, the co-character letters for UN is very simple. It's just n integers. It's just vector. Well, just letters of integers, n of them, and the while group just acts by permutations. So this is the simplest. Well, if you look at this particular charge, 1, 1, and less as zeros, or 2 and all possible zeros, then these seem to be good charges. If you compute the dimension, actually you get 0, not 1. And you want delta equals 1 scalars. Now, how compute dimensions is a separate story. I don't want to touch on that. That's actually rather non-trivial. But basically, there's some sort of Casimir charge. So that this delta or Casimir energy. So that, this is like a magnetic flux, and it distorts the vacuum, and then the vacuum when it's to cross R with flux has non-zero energy in general. In this case, though, there's constellation. Actually, that vacuum has 0 energy, even in the presence of this flux. However, these are not gauge invariant states yet because of this Chern-Simons coupling, and you need to add 2 charged guys precisely to cancel this electric charge to make everything gauge invariant. And it turns out these are the states you can construct, like for starting from this sort of naked states, vacuum states, and they transform in the right representations of the manifest R symmetry group. So, okay, they're all there, and then you can argue from that using just simple group theory that the whole multiplet is there in the undeformed theory. Like for Chern-Simons level 2, the situation is different. There, if you want to construct scalars with dimension 1, the only allowed charge actually is this one, 1, 0, well, 1, and there's a 0. And so there are fewer of these fellows. And then for k greater than 2, there are no such scalars at all. By the way, so why did I find, it looks like I found twice, well, in the k equals 2 case, I found precisely as many as I wanted. in the k equals 1 case, I found twice more. So what happens basically is the following, that in this k equals 1 theory, actually there are two copies of n equals 8 superconformal symmetry because the whole theory, non-perturbatively, decomposes into a free sector and the interacting sector, and they separately have n equals 8 supersymmetry. That's something non-obvious. Again, if you start with the classical Lagrangian, you can't see that. But the point is that there is on the quantum level, this interacting field theory decomposes a free field theory plus the rest, and they separately have n equals 8 supersymmetry. So you've got to have two copies of this. So you actually have two stress energy tensors, one for the free part, one for the non-free part, and two everything. And that's why I have also two of these scalars. So you can see all these things just by analyzing these monopole operators. Well, here's a further example where you have models with unequal ranks. So in this case, you can also construct the states, and you can argue, again, enhanced supersymmetry. Well, it seems like I can continue like that, but for example, why did they have n plus 1 instead of n plus anything? But actually turns out that some things go wrong if you increase the number of ranks, like you have monopole with negative dimensions, like that. So it's violating unitarity bounds. So this is the only case where it doesn't happen. So now ABGM, so they didn't just conjecture that this theory has enhanced supersymmetry, they conjecture that actually equivalent to super Young-Mills theories. And that can also be, well, you cannot prove that, but you can give additional evidence, which is quite non-trivial. Well, one I already mentioned, this theory, which corresponds to k equals 1 case, supposed to describe M2 branes in flat space-time. So the center of mass of this branes is decoupled. It's a free sector I was talking about. So you should be able to see that and receive. Now, another thing you can do, you can compute the partition function of this theory and compare with the partition function of super Young-Mills, well, the infrared limit of super Young-Mills theory. I don't want to go into this. It's, again, highly non-trivial, but they do agree. And there's some horribly complicated functions of a bunch of parameters which agree, which is non-trivial agreement. So again, it's not a proof of equivalence of the theories, but it's very strong evidence. Now, finally, an amusing tidbit is that super Young-Mills theories, of course, are parity invariant, and also their limits are parity invariant. So, but this theory, which is supposed to be dual to them, or some fixed points of them, it doesn't seem parity invariant. This theory is a parity invariant because if you do parity, the Chern-Simons level flips sign, right? But then you can sort of exchange the two factors, and you're still fine. Theory goes to itself. But for these theories with unequal rank, you don't go to itself. There's no symmetry in the classical level. So how can it be? Now, actually, it turns out that there is a non-trivial hidden sort of parity. There is some duality similar to level rank duality in 2 dimensions, or on cyberg duality in 4 dimensions, which is valid for generic n equals 3 theories, so with gauge group UN and matter in the defining representation. So you have UN theory level K with F copies of the defining representation, matter in that representation. Then it's actually believed to be isomorphic or to a similar theory with different gauge group, but the same number of hypermultiplets and also opposite level. Okay, again, it's a conjecture, but there's some massive evidence that's true. For example, the partition functions agree again. Now, if apply, well, you see the ABGM theory, this one, is a product gauge group, and the matter is in the product of a defining representation of the first factor and anti-defining of the second factor. So from the point of view of the first factor, just like these theories. So you're going to sort of dualize just ignore the second gauge group and just dualize the first one. From the ABJ theory with this gauge group, you're going to get to this one. There's some subtlety here, which I sweep under the carpet, related to Chern-Simons levels. Namely, what happened to this level? It was minus k. I didn't do anything to this factor. I just dualized the first one. So it became this. But how come this Chern-Simons level minus k became k here? Well, the subtlety. So I don't want to explain that, but it's shifted. The level of the spectator gauge group is also shifted. And the shift precisely shift by 2k in this case, and that's why it becomes like this. But anyway, so if you apply this to the special case of when the difference in ranks is 1 and level is 2, this duality maps this theory to the same theory with opposite levels. So that duality is actually non-trivial parity transformation, which is only visible in the quantum theory. Okay, so what we learned from this is it seems like there are theories with hidden supersymmetry, but the examples I gave, they seem to be, we don't have proof, but they seem to be isomorphic to the ones we already know, at least based on the level of things like partition functions, parity, that sort of things. So how about the other n equals 8 theories, the BLG theories, which corresponds to this gauge group? Maybe they are isomorphic to some other n equals 8 supersymmetry. Maybe overcounted. Maybe there's also isomorphic to something. Now, the moduli space in this case is different, and it's related to the dihedral group. I didn't describe what it is there, but you can easily guess, like in these other examples. Well, you have M2 branes moving on this orbifold, so for you have this kind of moduli space, and well, if you have a flat space, then just get this. Which generally is different from this one. So, however, the dihedral group becomes, well, for small values of k, it becomes, like Z2 cross Z2, for example, for k equals 2. So maybe one can conjecture that at least for small k's, maybe they're equivalent to something we already know. Again, it's kind of hard to figure it out, to prove this. So, but nevertheless, it seems like the following isomorphisms do hold. So on the left, you have these BLG theories. On the right, you have these other theories, which we already discussed. Now, actually, there are two versions of this theory. You see the one with gauge group SU2 across SU2, and the other one when you divide by the, diagonal subgroup of the center. Because the matter transforms trivial into this diagonal subgroup of the center, so you might or might not choose to divide by it, and that affects the theory. So, well, they have different moduli space actually. So, well, for these low values of level, you have some isomorphisms, and how do we know that? Well, we can, for example, again, compute the partition functions. Although it's not very sensitive in this case, but you can also do something else, like compute partition function on 2-sphere across S1. So it's the Hilbert space, of course, is horrible and complicated, but you can, again, using deformation to coupling, can argue that this trace, this weighted Euler characteristic, can be computed. And it's a function of variable x, and which single variable x is a bunch of variables z. As many, well, z lives in the maximal torus of the sort of symmetry group, of the bosonic symmetry group. So for example, for ABJ theory, there's only a single z variable. So you can, for example, go ahead and compare these indices for ABJ theory and this BLG theory, which are believed to be dual. And okay, we can't compute it exactly. It's some horrible series, which nobody knows how to prove that they're equal. But if you just, Laurent series, sorry. If you expand in powers, well, the power series in X, and each coefficient of the Laurent series in Z. So, but here is the computation. Actually, we computed actually to 4th order in X. I didn't have the space on this slide, so I omitted it. But so they all agree to this order. So that's very strong evidence that for example, these two theories, although they have totally different gauge groups, actually are equivalent, isomorphic. Okay, so what we learned from all this is that there are a whole bunch of n equals 8 theories. So far, all of them seem to be either isomorphic to these BLG theories, which have the gauge group SU2 cross SU2, or to one of these n equals 8 superangles theories. And then there are some non-trivial isomorphisms sometimes with other theories. But so the picture is not completely clear. Now, I want to say something about almost maximally supersymmetric theories. There's a notable gap. There's no known n equals 7 superconformal field theories. Now, there are different ways to argue that there are none. The easy way, I would say, well, on a classical level, you cannot write down anything with this much supersymmetry. That is, anything you can prove that anything you write down, it has n equals 7, it has n equals 8. But that's not very satisfactory, because as we know now, in 3 dimensions, sometimes symmetry is enhanced non-perturbatively. Some quantum effect through this monopole operators, for example. So how do we know? Maybe there's some theory which has classically has some lower supersymmetry, but quantum mechanics is enhanced to n equals 7. Now, actually, Dennis found a very simple argument showing that it cannot be. If you have n equals 7, then you have n equals 8 if the theory is unitary. And it's just an exercise in representation theory of the superconformal algebras. The first step in this proof is to show that any n equals 6 superconformal field theory has a U1 current, additional to U1 current, which commutes with SO6 generators. The way it works, you start with the superconformal algebra. It says that the stress energy tensor multiple contains also some scalars with dimension 1 and representation 15 of SO6. And then you act with two supercharges, and you can construct, first of all, the vector states corresponding to the R currents, or you can construct also another vector state which is actually commutes with the R current. Well, is the trivial representation of the R symmetry, and that is actually one current. You can show that its norm is non-zero just using superconformal algebra and unitarity, and then so it must be non-zero state, and therefore by state operator correspondence and non-trivial conserved current. So first you show that, and then so that any n equals 6 theory has actually extra symmetry, extra U1 symmetry, and then you can show from that that n equals 7 is actually n equals 8, has n equals 8 supersymmetry, because it just turns out to be inconsistent. This extra, well, you can say that n equals 7 theory also must have this U1 symmetry, and you can ask how does it commute with SO7 generators or not. Turns out that it can't not commute. So it cannot commute. It must be part of SO8, and then you have SO8 R symmetry and then n equals 8 supersymmetry. So simple arguments based on unitarity show that n equals 7 supersymmetry is not possible for unitary quantum field theory. Okay, so let me conclude. So, do we know all n equals 8 superconformal field theories? I don't know, because first of all, we looked at theories with n equals 6 supersymmetry and larger, and saw that sometimes it is enhanced. Okay, in that case, we have finite list. We can actually go through it. Well, not infinite list, but we can still go through it and show that this is the cases I described are the only ones where this happens. But there are many more theories with n equals 5 supersymmetry, even more with n equals 6, n equals 4 supersymmetry. Nobody went through this whole infinite list and checked whether all of them, or maybe, well, actually, we have one example where there's hidden n equals 8 supersymmetry, and n equals 4 enhanced to n equals 8. I don't know, maybe there's some other examples. Also, how about some non-trivial, non-perturbative isomorphism between known field theories? I don't know either. For example, if you look at G2 superangles theory, look at its moduli space, actually, potentially, it involves some dihedral group of order 6, so potentially it's due to some BLG theory at some level, which also has the same moduli space. I don't know if they're the same theory or not, but it's conceivable that they are. So I don't know about other superangles theories. They might also be due to some Chern-Simons theories. So it's still a mystery what's the classification scheme. Either is a simple classification scheme, unlike in 4 dimensions. Okay, so I'll stop here.
Questions?
N equals 3 in 4 dimensions is saying that.
Yeah, that's one of the similar results, by the way, to this
So
3-dimensional
right.
7 to n equals 8 enhancement.
And I think it's proven the same way. Almost. I mean, it's very long ago in Nash.
I think it's a bit simpler, actually. Yeah,
Is it
it's
simpler?
a bit simpler, but
But it's same lines.
CPT argument.
Right.
Here you don't use CPT, but it's similar.
What do you use?
I use unitarity. Yeah, it's similar flavor argument.
Other questions?